Hello. On today's video, we're gonna present from the book Experimental Methods for Engineers, Chapter 7, Flow Measurement. This chapter offered an overview on calibration of flow measurement devices, as well as the relative advantage of having different devices as ventorimeters, orifice, and flow nozzle meters, and the type of flow they measure with the most accuracy. Table 7.2 is the summary of several types and common numbers with flow meters. On table 7.2, as stated earlier, there is different types of meter types distributed alongside the table, and with their common values for maximum flow range, useful rangeability, maximum pressure, temperature range, maximum viscosity, their scale, their indication, their standard accuracy, construction materials, pressure loss, line size, special piping considerations, typical power requirement, and relative cost. This table is an overview of what we're expecting to see in the chapter with more certainty.
To start off this presentation, we'll first go into section 7.1 of chapter 7, flow measurement. The measurement of fluid flow is important in applications of various areas of study. It can range from medicine to engineering or any other field. In some cases, like medicine, we look into the blood flow rates in a human artery, or in our case in engineering, the measurement of flow of liquid oxygen that goes into a rocket. In some cases, extreme precision is used in the flow measurements, while in others, we only need crude measurements. And in flow rate measurement devices, they frequently require accurate pressure and temperature measurements to calculate the output of this instrument. The overall accuracy of the flow measurements start by the accuracy of some pressure or temperature measurements. Flow rate is expressed in both volume and mass units. Some commonly used terms like the gallon per minute, the liter, cubic foot per meter, and standard cubic foot per meter have their own units to solve.
The objectives of this presentation is to learn about different flow rate measurement devices, learn about their calibration standards, and discuss the different methods of calculation and flow visualization.
In section 7.2, it talks about how the flow rate of non-volatile liquids like water are measured through a direct weighing technique. The time to collect the quantity of liquid is measured, and an accurate measurement is then made of the weight of the liquid. This accuracy can improve by doing longer time intervals. Positive displacement flow meters are used for applications where high accuracy is desired under the steady flow conditions. As we see here in the figure 7.1, a typical positive displacement device is the home water meter, is the one we see here. This operates on notating this principle. Water enters the left side and strikes the disc that is mounted. The fluid moves while the disc wobbles to the vertical axis. In the figure 7.2, the rotary vanes are spring-loaded so that they continuously maintain contact with the casing of the meter. This eccentric drum rotates and the fluid eventually finds the exit. The uncertainties of figure 7.2 are around 0.5%. In figure 7.1, it's within 1%. In figure 3, the lobed impeller meter can be used for either gas or liquid flow measurements. The impellers and case are carefully machined so that the accurate fit is maintained. In section 7.3, we see that there are several types of flow meters that fall under the category of obstruction devices. These are commonly known as differential pressure meters also. Such devices are called head meters because of the head loss or pressure drop measurements that are taken as an indication of flow rate. As we see here on the center, we consider the one-dimensional flow system with its continuity relation, where U is the velocity. If the flow were to be adiabatic and frictionless, the fluid is incompressible, so the familiar Bernoulli equation, as we've seen in other courses, is shown, where now the pressure 1 is equal to the pressure 2. This gives the pressure drop, as we see on the third step. And we see on the right side that the bolometric flow rate may be written as Q equals the way it's expressed there. And we see here in the channel shown above, this could be used for flow measurement by simply measuring the pressure drop and calculating the flow. However, by being frictionless, some losses are always present in the flow. This volumetric flow rate shown here is the ideal value and is usually related to the actual flow rate and an empirical discharge followed by the equations that are shown in this chapter. In the section 7.4, practical considerations for obstruction meters, the construction of obstruction meters have been standardized by the American Society of Mechanical Engineers. The recommended proportions of Venturi tubes are shown in the figure 7.6. If you didn't know, Venturi offers the advantages of high accuracy and small pressure drop, while the orifice is lower in cost. To continue, when the pressure taps are connected to the manifolds, which surround the upstream and throat portions of the tube, these manifolds receive a sampling of pressure in all sections of so that the good average value can be obtained. The discharge coefficient, however, is smaller for pipes less than 2 inches in diameter. For a more precise value in the discharge coefficient for a Venturi tube, and this gives us the accuracies of more or less 0.5%, which is better for us.
Good morning, my name is Jesus Agora Sanchez, and I'm going to present the part of particular considerations for obstruction meters. The first graph is discharge coefficients for the Venturi tube. According to reference 1, values are applicable for 0.25 until 0.75. The second graph is approximation Venturi coefficients for various throughout diameter according to reference 15. The numbers on the curves are upstream and throughout diameters respectively. The next graph that we're showing now is the discharge coefficient for ASME long radius nozzle. In this chart, graphic, it has 3 standards set of pressure taps. The first one is both pressure taps are installed in flange as shown. The second one is the inlet pressure tap is located 1 pipe diameter upstream, and the outlet pressure tap is located 1/2 diameter downstream. Like I said, it's shown in the graphic. As you can see, the separations of each line. The inlet pressure tap is located at 1 pipe diameter upstream, and the outlet pressure tap is located at the vena constructa of the orifice. The second graph is the flow coefficient for concentric orifice in pipes. In this graph, we can see the ratio of the orifice in diameter to pipe diameter and the flow coefficient MC. Next, we have two graphics. The first one is adiabatic expansion factors for use with Venturis and flow nozzle, calculated from equation 7.14. The other one is expansion factor for a square edge orifice with pipe taps, as calculated from equation 716. So in the figure 7.14, there's a formula that it was supposed to be there, but it's not. So I'm just gonna brief you on it. It's supposed to be the various flow coefficients are plotted as a function of Reynolds number, and it's defined as Re equals the fluid density times mean flow velocity times diameter at the particular section for which the Reynolds number is specified, divided by dynamic viscosity. So next we have the sonic nozzle. This part is when the flow rate is sufficiently high, the pressure differential becomes quite large. It maximums value for the given inlet condition for an ideal gas with constant specific heat. Assuming isentropic flow, the formula for this part is the one that is there. I can't say it very well, but you get it. This ration is called the critical pressure ration. Inserting this ration in equation 7.8 give us the mass flow rate as the equation formed there. So basically, it's the equation of 7.8 plus the equation of isentropic flow. So we unite them to make one. So in this part of the work, we're going to show the flow measurement by drag effect rotometer. So the rotometer is very commonly used for flow measurement devices, and is shown in the schematic in figure 7.16. So basically, the position of the bob is taken as an indication of the flow rate, and device is sometimes called an area meter. So basically, the things that are written there is the explanation given by us by the chapter. It's just explaining the figure. You can see the flow that is going up, the bob that inside a can, I think. We're given the diameter. It's holded by a taper tube. A force balance on the bob is given as Fd plus rho F multiplied by Vb multiplied by G divided by Gc. The G's are the gravity, equals rho F times Vb divided not divided G divided by Gc. So it's the same thing on the other side without the force. Well, force no, the flow. So now I'm gonna leave you with the other companion.
The rotometer. The rhodometer is a flow measurement device in which flow enters the bottom of a tapered vertical tube, which causes the flow to rise to the point where the buoyancy forces are balanced. The equations shown describe the phenomenon occurring inside the tube, where U is the velocity and A is the area of the tapered tube. Turbine meter. A turbine meter is a flow measurement device in which fluid moves through the meter, causing rotation on the small turbine wheel. A pickup is attached to detect the pulse of every rotation. The equation shows the flow of the fluid inside of the meter. Vortex shedding flow meter. The vortex shedding flow meter is a flow measurement device in which a fluid stream is separated. This causes a vortex, which is later analyzed to obtain the instantaneous flow rate. The equation shown, also known as the Strouhals number, which is represented by the letter S, where Fs equals to the shedding frequency, d equals to the diameter of the control volume, and u equals to the velocity of the fluid. Ultrasonic flow meter. The ultrasonic flow meter is a measurement device in which an ultrasonic frequency is transmitted through the fluid. Discontinuity on the fluid will reflect the signal, which will indicate the proportional velocity. For this, we will use the equation shown, where the Reynolds number should be smaller than 2000. After that, the flow and the mass rate can be calculated. Hot wire and hot film anemometers. This device consists of a heated electrical wire placed in the steam flow, which reads the heat transfer rate from the steam. The equations shown are two different equations. The first one will apply to the temperature of a fluid, and the second one will apply to an electric current.
Thermal mass flow meters is a direct measurement of mass flow of gases. The way it works is a percussion tube is constructed with the upstream and downstream externally wound-resistant temperature detectors and an electric heater between the sensors. An appropriate bridge circuit detects the mass flow of the gas, which is directly proportional to the temperature difference T1 minus T2. Another type of thermal mass flow meter for gases uses two platinum RTDs, with one sensor measuring the temperature of the gas at the point of immersion, and the second sensor is above the first and heated to a temperature of 60 degrees Celsius, which is transferred to the gas because of the gas flow and convection. The heat transfer rate is proportional to the mass velocity of the gas, defined as mass velocity equals density times U, in this case meaning velocity. Turbulence measurements. In turbulent fluid flow, whether in a channel or in a boundary layer, the fluid velocity components exhibit a random oscillatory character, which depends on the average fluid velocity, fluid density, viscosity, and other variables. The instantaneous velocity components are expressed as what follows, where the bar quantities are the integrated average velocity components and the primed quantities represent the fluctuations from the average velocity. The figure 7.26 illustrates a typical plot of turbulent fluctuations. One measure of the intensity of turbulence is the root mean square of the fluctuations, and the average kinetic energy of turbulence per unit mass may be taken as a measure of the total turbulence intensity of the flow stream. The hot wire or hot film anemometer is very useful for turbulence measurements because it can respond to very rapid changes in flow velocity. The way this works is two or more wires at one point in the flow can make simultaneous measurements of the fluctuating components. Various mean values and energy spectra can then be computed from the voltage outputs of the probes. In general, these measurements can be performed electronically. The values underneath figure 7.26 describe the typical values of range of turbulent fluctuations. In magnetic flow meters, you can consider the flow of a conducting fluid through a magnetic field as shown in the figure at the right, 7.27. Since the fluid represents a conductor moving in the field, there will be an induced voltage according to the equation below. The length of the conductor is proportional to the tube diameter, and the velocity is proportional to the mean flow velocity. The two electrodes detect the induced voltage, and that is used as a direct indication of the flow's velocity. Two types of magnetic flow meters are used commercially. One type has a non-conducting pipe liner and is used for fluids with low conductivities like water. The second type of magnetic flow meter is one which is used with high conductivity fluids, principally liquid metals. These are magnetic flow meters. Flow visualization methods. Flow visualization by optical methods offer the advantage that when properly executed, it does not disturb the fluid stream, and thus gives the experimentalist an extra tool to use in conjunction with other measurement devices. An incoming light ray is deflected. The deflection of this angle for small density gradients is given as the incoming light ray is deflected through an angle epsilon as a result of the density gradients in the flow, where L is the width of the flow field, rho is the local fluid density, rho sub S is a reference density which is usually taken at standard conditions, and N is the index of refraction, which for gases may be written equating to N. To study the flow phenomena and visualize it, a typical experimental technique is to add a dye to the liquid. The other technique in figure 7.29 uses a fine wire placed in water as one end of the DC circuit electrolyzes the water. This forms small hydrogen bubbles in the liquid, and the motion of the bubbles may be studied by illuminating this flow. The shadow graph technique. This is a method for direct viewing of flow phenomena. The flow field shown in figure 7.30, you can see a density gradient in the y direction. The parallel light rays enter the test section as shown. In the regions where there is no density gradient, the light rays will pass straight through the test section with no deflection. For the regions where a gradient exists, the rays will be deflected. The effect of this is that the rays will bunch together after leaving the test section to form bright spots or dark spots. The illumination will depend on the relative deflection of the light rays. The illumination on a screen placed outside the test section is dependent on the second derivative of the density at the particular point. This phenomenon is visible because of the density gradients that result from the heating of the air near the hot surface. Figure 7.31 illustrates the free convection boundary layer on a horizontal cylinder. The dark area is the boundary layer and heated wake above the cylinder. The halo results from the refraction of the light pencils nearest to the heated surface. The distance between the cylinder surface and the halo at the same angular position is proportional to the surface convection heat transfer coefficient.
The interferometer is the most precise instrument for flow visualization. It is used to obtain the direct measurement of density variations in the test section. The changes are picked up by fringes creating an optical path of light that gets interrupted with changes in the test section. This change can be calculated by the first equation in the presentation, and then that change can be related to the density for gases given by the second equation. The number of fringes shifts, it is given by the third equation presented. The figure 7 7.35 is the interferometer photograph of an interaction of three convection boundary layers on three horizontal heated cylinders. As you can see, fluid is air, and each fringe is a line that represents a line of constant temperature. The figure 7.34, it is a schematic of the Mach-Zehnder interferometer that has a light source, two beams, and a test section, which has different measurements as L1, S1, M2, M1, S2, and L2. All of this is the test section is a flow field, which is then projected in a screen. The laser Doppler anemometer, or LDA, is a device that offers non-disturbance advantages of optical methods while affording a very precise quantitative measurement of high frequency turbulence fluctuations. This device must be constructed so that the direct scattered beams travel the same optical path in order that an interference will be observed at the photomultiplier tube that is proportional to the frequency shift. This shift then gives an indication of the flow velocity. To retrieve velocity data, the electronics techniques must be employed for signal processing. A spectrum analyzer may be used to determine the velocity in the steady laminar flow as well as mean velocity and terminal intensity in turbulent flow. The laser beam is split outside the test section, and then two beams can be focused on the exact same point to be studied in the flow field. Pressure probes are used in applications involving external flows, such as aircraft or wind tunnel tests, where another measurement is required. Probes must be inserted in the flow to measure local static and stagnation pressures, which leads to the calculation of local flow velocity. A typical probe used is the pitot tube. It has an opening in the front which senses the stagnation pressure, while the small holes around the outer periphery of the tube senses the static pressures. And the total pressure for isentropic stagnation of an ideal gas is given by the first equation stated in the presentation, where M is free stream Mach number, which is given by the second equation. The third equation is the acoustic velocity, and it may be calculated with that equation. For an ideal gas, it has to be converted in terms of dynamic pressure, which can be defined by the fourth equation, and the first equation becomes then the fifth equation for gases, and this relation may be simplified to the sixth equation, where the Mach number for stream velocity can be stated with the seventh assumption, with the seventh equation, which is an assumption. For a very small Mach number, the equation reduces to the familiar incompressible flow formula, which is the eighth equation stated in this slide. In this slide, we have a few of the measurements taken by probes. As seen in the figure 7.38, the stagnation pressure response of various probes is channeled as a parabola influence given by the equations stated above in the other slide. In figure 7.40, we can see the schematic for a pitot tube, which is the most common pressure probe, which is very useful to have. In figure 7.41, a variation of static pressure along standard subsonic and supersonic probe types is given, with the equations stated in the other slide as well. As seen As seen in this slide, it is very useful to have these graphs, since it's very visual and very and it can be a useful tool to measure flow. For impact pressure in supersonic flow, a shockwave will be formed in front of the probe, and the total pressure measured by the probe will not be a free stream total pressure before the shockwave. Still, it is possible to express the impact pressure of the free stream static pressure and the free stream in Mach number. The resulting expression is stated in the slide, and this is all. This equation is valid for Reynolds number based on the probe diameter greater than 400, which is called Rayleigh supersonic pitot formula. To conclude, this chapter completed all the objectives teaching about the different flow rate measurements devices, as well as their calibration and visualization methods. Based on the chapter, probes are the most efficient and accurate at measurements with any type of flow they are exposed to, thanks to visualization methods like the interferometer or the shadow graph make a particle perception of what is going on with the flow, which is imperative to create a fundamental picture of the flow. Every flow meter has its use, and it's crucial to be precise when working with flow on any controlled environment.